Okay, so welcome everyone to this week's seminar. We're very happy to have Arthur Gretton who's going to speak. So Arthur is a professor at the Gatsby Computational Neuroscience Unit and the director of the Centre for Computational Statistics and Machine Learning at UCL. He did his undergraduate degree at Australian National University and a PhD from Cambridge. And since then, I think spent some time in industry and postdoc at Carnegie Mellon University. I think, yeah, now it's at UCL. So we're very happy to have Arthur. He's going to talk about generalized energy-based models. So please feel free to ask questions during the talk, either via the chat, or I think Arthur's very happy for you to interrupt him and just sort of speak out loud if you rather do it that way. Yeah, so over to you, Arthur.
Yep. So thank you for the invitation. So the talk's on generalized energy-based models. This is a work that appeared at ICLR, the machine learning conference earlier this year. And so the two people on this slide, Michael Abel and Yang Zhou, are authors on this with me. So definitely, please, I have the chat window open, so please interrupt me if you have any questions. I'm happy to read them off the chat or be audibly interrupted. I think we can try and make it as close to a live talk as possible. So I like to have questions. Right. So I think theme of this talk is this notion of training generative models. So what this means is that we have some collection of samples from some unknown distribution, which I've written P, and the goal is to generate samples from some artificial distribution Q that look like, in some sense, P. And the challenge here is that our samples are going to be structured and in very high dimension, for instance, images. So here is an instance of that, where we've got our samples from P are images of bedrooms, our samples from Q are artificial images of bedrooms. And the goal of this learning is to get these Q samples as close as possible to the target P samples. Now, since we're comparing, we're comparing artificial samples to real samples, we need some notion of loss, something that we can use, some signal we can use to train our Q. And this training signal is going to be some measure of divergence between P and Q. So a measure of divergence between the distributions P and Q, which is going to tell us when it is that the Q distribution is close to P. So when our artificial samples, our fake bedrooms, look like our real bedrooms. Okay, so this is at a high level the theme. Now, where we're going to be starting with in this talk is one of the most, I think, popular machine learning techniques for generating artificial samples in high dimensions with structure, which is the generative adversarial network. So here is our little cartoon reminder of what a generative adversarial network is doing. On one hand, I've got my generator. So this is the artist here, which is generating artificial samples, in this case, fake dogs. And then I have my critic, which takes my set of fake dogs, my set of real dogs, compares them, and gives some feedback to my generator, which the generator then tries to improve. So the generator tries to minimize this divergence between real and fake dogs. And this process iterates until equilibrium is reached. Okay, so this is at a high level in diagrammatic form what is going on with a generative adversarial network. So key to this generative adversarial network, of course, is the critic. So the critic that compares the real to fake dogs and gives feedback to my student. And this will be the focus of this talk. Okay, so we want a measure of divergence between sets of objects. There are two broad families of divergences that I'll think about here. One is the integral probability metrics, and the other are the phi divergences or F divergences. And where I think my first provocation is going to arise in this talk is to argue, on the one hand, that phi divergences are a terrible idea, and that if you're using them, then they probably aren't working. But then to perhaps argue that phi divergences, as used in practice by, let's say, machine learners, turn out to be a good idea because a bound on those phi divergences is used that makes them act more like integral probability metrics. So that's my first provocation. And that's the first half of the talk. Then the second half of the talk, which basically aims more towards the title of the talk, is to introduce this notion of generalized energy-based models. So at a high level, what they're doing is that they're using the divergence as part of the sample generating process. So if we look how the critic function, so our divergence is used in a classical GAN, the critic has no say in the generation process, right? The critic is just giving feedback to the student, but the student does the generation on its own. And what I'm going to argue is that if we incorporate the critic into the generating process, then all else being equal, we are going to get better samples than if we didn't. So that's the second part of the talk. All right. So this is the outline. Okay, so let's start with our divergence measures. So let's say we have two distributions. So at a high level, there are two ways that we could compare them. One is to subtract one from the other, P minus Q in some sense. And the other is to take in some sense a ratio of P to Q. So if P minus Q is 0, or if in some sense to be defined, the ratio of P to Q is 1, this amounts to P and Q being the same. So these two ideas give rise to two families of divergences between probabilities. If we take as our starting point the difference of P and Q, we get the family of integral probability metrics. So, if we have a difference, we need to witness the difference in some sense. And so how we're going to do that in practice is to look for a function, G, in some family of functions, H, that maximizes the difference in expectations under P and Q. Now, the phi divergences are the ones that are based on the ratio. What we're going to, for the purposes of notation here, assume that P and Q have densities with respect to Lebesgue, and that the ratio of P to Q is well defined. In this case, I'm going to take the expectation of some function of the ratio of P to Q, and that's going to be my divergence measure. So this function is going to have a couple of properties. One is that if the ratio of P to Q is 1, then that function had better return 0, because then P and Q agree. It's also going to be convex and lower semi-continuous for reasons that are going to be clear later in the talk. Okay, what you'll notice here in this figure is that there is an overlap between these two spheres. The only non-trivial divergence that lives in this overlap is the total variation distance, so the L1 distance between P and Q. We're not going to worry about that for this talk, but I'm just going to alert you to that. Yeah. All right. So let's start on the left with the integral probability metrics. So these include the Wasserstein and MMD. So let's see what our function classes are for these. First of all, the Wasserstein distance. So in this case, the set of well-behaved functions that we're using are the functions whose Lipschitz norm is upper bounded by 1. So basically, the fx minus fy divided by norm of x minus y, sup over x not equal to y, should be upper bounded by 1. And I've shown here an instance of this witness function for a very simple example of P and Q. And what we notice here is that my red samples approach my blue. So as my generator, my fake samples approach my real samples, the Wasserstein distance is going down. So what we're showing here is that as the red converges weakly to the blue, my Wasserstein is going down. This indicates that it's a helpful critic witness. So in a sense, if I'm using this to give feedback to my generator, as my red approaches my blue, I can be assured that my witness function is giving me helpful feedback and showing me that this is the case. So it's decreasing, my distance is going down. Now, this is not a tutorial on optimal transport, so there's a great deal of work elsewhere on that, and I encourage you to watch those tutorials or read that literature, but I'm not going to talk about this further. The maximum mean discrepancy is another instance of an integral probability metric, where here we're using a unit ball in a reproducing kernel Hilbert space. And in this case, my function is smooth. It's well behaved in a way that I'm not going to go into in too much detail here. But again, we've got this nice property that subject to a sufficiently rich RHS, as my red converges weakly to my blue, I know that my MMD is going to go to 0. So it's going to metrize weak convergence subject to a sufficiently rich function class being used. So it's again a helpful critic witness function. Okay, So we can sort of see what the integral probability metrics are doing. They're finding a well-behaved function which has a large positive amplitude on my blue points, a large negative amplitude on my red points, and that it's trying to sort of find the function from some class of well-behaved function that maximizes this difference in expectations. But what we observe here is that because this function is well-behaved, it's sort of aware of the topology of the space. So it's sort of noticing when it is that red approaches blue. Okay, so this is at a very high level what the integral probability metrics are doing. What about the phi divergences that are based on this ratio? Just as a reminder, the phi divergence between P and Q is the expectation under Q of phi of P on Q. Phi is convex, phi of 1 is 0, and there's this continuity property that is going to be useful to us later. Probably the best known phi divergence, and certainly the one that we began to use throughout this talk, is the KL divergence. So the KL divergence uses phi of u as u log u. So this is our divergence measure. Okay, so let's say that we're using the KL divergence, and our goal is to use this divergence as a way of training a generative adversarial network. What might happen? So here is an instance. These are actually the density functions generating on one hand blue points and on the other hand red points. And in our figure here, I've shown the density functions rather than showing points drawn from them. And in this instance, the sample, or rather the support of the blue and the red is disjoint. Okay, so the ratio of P to Q isn't defined here. And in this case, the KL is defined to be infinite. The Jensen-Shannon, which is a sort of symmetric version of KL, so it's basically P on P plus Q on P plus Q. That's the sort of like Jensen-Shannon divergence that you use, is log 2. So it's constant, regardless of whether red is approaching blue, as long as the support of red and blue is disjoint. So this is arguably an unhelpful critic witness, because basically, as long as the support of red and blue is disjoint, then the critic is giving me no feedback whatsoever as to how or whether red is approaching blue. So, I'm presumably, this counts as improving my sample, and yet my KL is still infinite, my Jensen-Shannon is still log 2, and it's not telling me anything about how close red is to blue. Now, this situation where the sample support, where the support of P and Q is disjoint, is arguably what always happens in high dimensions. So there is this nice paper by Martin Nawjowski and Elbo Tu here, who argue that, let's say the goal is to generate pictures of bedrooms. So I've got a distribution P in a very high dimensional ambient space, occupying a very low dimensional support in that high dimensional space. And then I've got Q, which is my, my GAN generator, my artificial samples. The chance of the artificial samples being able to match the support of P is pretty much 0. So I'm going to always be in this situation where the support is disjoint. And so therefore, a phi divergence is always going to be useless. And so you should always use integral probability metrics. So this is, I think, a very convincing argument. And yet, let's say the great majority of all generative adversarial network papers are using what they claim to be phi divergences. So evidently, something's going on, but it's perhaps not a KL divergence. So then, what are people actually doing as opposed to what is claimed? So that's the topic of the next slides. Are there questions about that before I go on?
Can I ask a quick question? I guess so. I mean, if one takes like the Wasserstein distance and regularizes with entropy, then of course you get a KL divergence. Then of course this is kind of approximating the Wasserstein distance too. So I mean, like, yeah. So I guess I don't know. Can you kind of comment on that?
Oh, yeah. So no, that's a very interesting question. So Wasserstein, I think we know that, for example, in to compute the Wasserstein, I think you have let's say a very high cost computationally as V increases. And so Marco Couturi has done a rather beautiful work on a Sinkhorn approximation to the Wasserstein distance using a regularization, which is entropic. What's interesting is that as one increases the regularization, this Wasserstein approaches MMD, which is obviously another IPM with somewhat different properties. So I think the interpolation between MMD and KL is a topic which we will talk about shortly in a couple of slides. But when one looks at Wasserstein GANs in practice, in fact, Marco has done a Wasserstein GAN using the Sinkhorn approximation of the Wasserstein distance. So absolutely, you can do that, and it's a it's a good idea. Yeah.
Okay, thanks.
Are there any other questions? Okay. So basically, we've hit a dead end. We've said, I want to use KL to train a GAN. However, I've argued that KL is a terrible divergence and it's never going to give useful feedback. By the way, this cartoon is a sort of angry teacher that always yells no at you, whatever you do. So this is what the KL is doing in this case, because whatever, I'm placing my red closer to my blue, but because this board is not overlapping, I'm getting no helpful feedback in this case. Okay. So to describe actually what's going on, I'm going to need a brief divergence interlude into some notation, and then I'm going to return to the phi divergences. So the notation that I'm going to introduce is this notion of the conjugate or eventual dual of a function. So I've got my function phi here, which is u log u for KL, and the dual of this function is the slope-intercept form of this function. So basically, if I want to compute my dual of my function phi, the dual, I give it a slope. It finds the tangent line at that slope, and it gives me the negative intercept. That's the dual. Okay. And if my function is strictly convex, then the slope-intercept form is unique. For every value of the slope, there's a unique negative intercept. So this is a completely equivalent representation of my original function. Okay. And in particular, if phi is lower semi-continuous, which we know it is, we have the property that the dual of the dual is my original function. So I've got my slope-intercept form. I take the slope-intercept form of the slope-intercept form. I get my original function back. So this is sort of saying that I can express my original function as a solution of an optimization problem at every x. Okay, which sounds like I'm just playing mathematical games for the moment, but bear with me for another slide, and we'll see where this is useful. Okay. Now for the KL divergence, just for context, when phi of x is x log x, with a very small amount of algebra, you can find this slope-intercept form of it, which is e to the v minus 1. Okay, it's pretty straightforward to do. Okay, so this is the dual. Let's now use it to see what people are really doing when they say that they're using a phi divergence as a GAN critic. So here's my phi divergence, expectation under Q of T on Q. Now I'm going to replace phi with this optimization problem. So for every value z at which I'm evaluating my function, phi of pz on qz, I'm going to solve a different fz. So I'm, for every value z, I need to solve a different optimization problem. And if I do that, I get back my original function. So this is just the result from the previous slide. And this phi star is the dual function of phi of x. Okay, so far I've done nothing, right? I've replaced the function with the same function. But now what happens if rather than solving exactly for every z, I solve approximately, right? So I require, in addition, that this function f should be a smooth function. Well, if it has to be a smooth function, I'm not going to be able to get the fz, which is the perfect solution at every z. Instead, I'm going to get a lower bound, okay? And with a small amount of rearrangement, I get sup over f, which is now a smooth function of z rather than being an arbitrarily non-smooth function of z, of EP of f minus EQ of p star of f. Okay, I'm getting this by restricting the function class, requiring f to be smooth. Okay, now the bound can be tight if my set of functions, calligraphic h, is rich enough. In particular, it needs to include the derivative of phi, I'm assuming here that phi is differentiable, evaluated at p on q. So if my f is rich enough to contain this, then I'm going to be able to get a tight bound. Okay, so let's see what happens when we use the KL. Here's the KL, log of p on q, integral of p dz. I replace my phi function with this optimization problem, recalling this dual form here, phi star of v is e to the b minus 1. So this is where this e to the minus f comes from. So just as a sort of point of clarification, I've got ep of f minus eq p star of f. Here I'm using as my function class minus f plus 1 for reasons that will make notation simpler later in the talk. Okay, but I'm doing exactly what I talked about in the previous slide. Okay, when is this bound tight? It's tight when f can be equal to the negative log ratio of p to q. Okay, so if my function class is rich enough that it contains the negative log ratio p to q, then my bound becomes tight. Here is an example when p and q are both Gaussian, negative log ratio is just a straight line. When p and q have the same variance and different means. So that's, if the straight lines are in my calligraphic H, then I'm able to make my bound tight for two Gaussians with different means. Okay, what happens now if I'm computing for samples? Well, this actually is rather easy. If I've got IID samples from P and Q, I just replace my expectations with sample expectations. And that's the answer. Okay, so this gives me my KL approximate lower bound estimator, which we're going to call the KL divergence. So the KL divergence here is an approximation, like a sample approximation to a lower bound on the KL. And this is, what people use in practice when they're using a phi divergence to train a GAN. They don't use the phi divergence, they use a lower bound on the phi divergence. Now, arguably this lower bound, because this function f is a smooth function, a well-behaved function, it starts to look more like an integral probability metric. It starts to behave more like an integral probability metric. So let's go somewhat close to the case of the MMD. So I'm going to use a reproducing kernel Hilbert space, so same function class as I did for the MMD. But in this case, I'm going to use it to solve this optimization problem here. Okay, this is a simple quadratic program. If you want to see how to do it, I've given the reference below, but I won't dwell on that for this talk. Okay, so because we have this smoothness penalty, we're going to call it the KL smoothie. Here is the witness function that solves this problem for the example that we gave in the previous slide. Well, some slides ago. Okay, so f is a smooth function that maximizes EPF minus EQ of e to the minus f. So see the difference here between the MMD. The MMD would have EP of f and EQ of f. Here I've got EPF and EQ e to the minus f. Okay, not quite the same thing. But you can see that because we've required f to be smooth over space, it's actually a helpful critic witness. So on the one hand, it's well defined when blue and red have disjoint support. And on the other, as red approaches blue, this is decreasing in a well-behaved way. We're going to make this formal shortly, but I'm just showing you intuitively what's going on. So in this sense, this lower bound using a well-behaved class of function is acting like an integral probability metric rather than like a phi divergence. So hopefully that answers the question from earlier of like in what sense is the MMD and the KL related. What I will now reveal, and this is in this paper cited below, is that as we increase the amount of penalization, this KL actually approaches MMD. So indeed, we are getting closer and closer to MMD as we increase this penalty here. That's in this paper here. So this is actually a very recent result that was published in June. Yeah. Okay. So it seems that in some sense, we've won by replacing our KL with this lower bound. But I want to sound a little note of warning here. Here is the note of warning that there are certain, let's say, dissimilarities between P and Q that are not well detected when we use the lower bound that we've chosen to use. So here is an example. Let's say that I've got my two Gaussians, and let's say now that the KL is well defined. So I've got my two Gaussians. Well, the KL is always well defined because the ratio is always well defined. In this case, so I've got one Gaussian that is going to have a much narrower variance than the other. Okay, so as I move up my x-axis, my red Gaussian is getting narrower and narrower with respect to my blue Gaussian. So this is called mode collapse in the GAN terminology. It means that the samples that we're generating are more and more focused on the mode of the data distribution, which is not great because it means that you're effectively generating the same picture over and over again in the limit. Now, as we have this collapse, we can see that our KL is going up. Okay, so in this green line here, this is in a sense what we would like our divergence to do. Which is that our KL, our variation of lower bound, should increase exactly in step with our KL. However, that's not what happens, right? What we observe is this orange line here, which is that the KL, the lower bound, is going up a lot slower than it should. And the reason for this amounts to this issue here that we came to earlier, that the bound can only be tight when the F contains the negative log ratio P to Q. Now, as the red becomes very, very narrow, this negative log ratio becomes non-smooth, and I'm not able to represent it well with the functions in a smooth function class. So that means that my bound diverges from the real KL. So this is a mode of, let's say, a failure mode, which our KL is less sensitive to than it should be. All right. Any questions about this or about anything so far?
So just so I can make sure I can understand. So the KL is a lower bound, right, and KL.
Yep.
Okay, right. Okay, and so
so it's a lower bound that we get basically by solving this basically optimization problem imperfectly. So rather than solving it exactly for every z, we're going to say we'll solve it as well as possible, subject to f being a smooth function of z.
Okay, right. So on your graph, the observed and the true. So is this is the observed? Is this the empirical approximation?
Mm-hmm.
Or
right, exactly. So, in practice, we are going to have samples. So samples of, let's say, our real bedrooms, and then samples generated from a model of our fake bedrooms. And we are able, nonetheless, to compute this because effectively we've just got expectations. So we just replace them with sample expectations. Yeah.
Okay, so that's the difference between the two curves, right?
Yep. Yep. Yeah, exactly. So effectively, what I'm computing here, like this plot here, I'm computing this using the samples for a particular class of well-behaved functions, namely the reproducing Helmholtz spaces, because then it turns out that it's a rather easy quadratic program to solve to get this function, given samples from P and Q.
Okay, thanks.
Yep. So this is sort of what's going on. But the sort of key point here is that because this function is smooth, which it doesn't matter that the density ratio is ill-defined or undefined in this case. This smooth function nonetheless detects the difference in P and Q, and importantly ensures that the KL, our lower bound, the upper bound here is vacuous; it's infinity, right? For both of these sets of points. The lower bound is informative because the lower bound is telling me that red is approaching blue. So, you might argue, well, why would you use a lower bound on a quantity you're trying to minimize? And my answer to that's actually you right here asked me that question. And the answer is, well, the upper bound is meaningless here, but the lower bound is informative. And in fact, the lower bound is, gives a class of divergence measures that is actually useful for this class of problems, whereas the upper bound is a family of divergence measures that isn't useful. It's not, I'm saying it's sort of like an IPM, like an integral probability metric, but it's not quite, because there is an asymmetry in P and Q here, whereas an IPM is symmetric in P and Q. However, one thing that we show in this paper is that as you increase the amount of smoothing that you enforce, you get something that approaches an MMD. So it approaches an IPM. That's beyond the scope of this talk, but something that I just wanted to sort of mention here. Okay, are there any other questions? Okay, this talk's much too easy. All right. So I've sort of talked in a rather hand-wavy way about this notion that the KL behaves like an IPM. I want to now make some of these properties a little bit more formal. Okay, so on the one hand, I want to ensure we know that, for instance, the KL is non-negative and is 0 only when P and Q agree. We have just proposed a lower bound on the KL. And a first question might be, well, does this lower bound still satisfy that property? Because this is an important property. I want my KL to be, or my KL, rather, my lower bound to be 0 only when P and Q are the same. Now, it so happens that if I have a rich enough function class, then it does satisfy this. So for example, if my H is a reproducing Konohovec space and it's characteristic, which means that the MMD is 0 only when P and Q are the same, then the KL is 0 only when P and Q are the same. So this is one function class that satisfies that. So if I use a RKHS with a Gaussian kernel, that satisfies that property. If I use as my function class this neural net function class, so the span of a ReLU, a rectified nonlinearity, on affine transforms of my data. So if this is my set of basis functions, then this is also rich enough to ensure that KL is 0 only when P and Q agree. So that's the sort of like minimum requirement for a neural net function class to ensure this property. Okay, so this ensures that my KL is 0 only when P and Q agree, but it doesn't give me another very important property, which is that I want my KL to metrize weak convergence. So I want that, as Q converges weakly to P, I want my KL to go to 0. Now, this requires an additional property of my function class, that it should be Lipschitz in the inputs with constant L. If this additional property is satisfied, then I have this property that KL goes to 0 if and only if Qn converges weakly to P. And this property makes it, I think, very clear the sense in which the KL relates to IPMs, because to prove this makes this construction explicit. So here is the proof sketch. Okay, here is my KL. In the case of the KL, so I've got minus FDP minus e to the minus FDQ plus 1. Then what I'm going to do is to add and subtract the expectation of F. So I'm going to add it here. I'm going to subtract it off here. Okay. And then I remark that this quantity here is non-negative. So its integral is non-negative. And so I can therefore upper bound this by integral of FDQ minus integral of FDP, which, if this Lipschitzness constraint holds, is in turn upper bounded by L times the Wasserstein distance. So when Wasserstein goes to 0, this forces KL to go to 0. And we know that Wasserstein goes to 0 when Q converges weakly to P. So this is the sense in which the KL acts like an IPM. We can upper bound KL by an IPM, and this then has the implication that we like. Are there questions about that?
So does this mean you have to impose the condition then that all functions in your class are Lipschitz? Or... Yes,
that's right. That's right.
Does it not hold without? I mean, is this property false without the Lipschitzness?
So without the Lipschitzness, this proof wouldn't work. but it's an interesting thought, actually, whether one could nonetheless show that a property like this will hold. I wouldn't, for sure, our proof just uses the licentiousness. It's a
somehow I would expect that the density of H in C should already be enough. But that's
right,
without thinking
you've
at all
got
about
the, yep, no, the Dudley result, right? That if you're dense in the space of continuous functions, then you're able to approximate this, yeah. That's a good point. Right. Which would be true if F was in the universal RKHS, which are dense in the space of bounded continuous functions on compact domains. So yeah, so I think that would also be a way to do the proof. Yep. Yep. Okay. Good. So now that sort of ends the discussion of critic functions, and now we turn to generalized energy-based models. So at this point, we've talked a lot about critic functions, but now we're interested in the whole process of generating samples. And recall from again that we've got our generator generating samples, our critic that compares real to fake samples, and once we've sort of trained our GAN, we take our critic and throw it in the bin, and then we are left with our generator. But this seems very wasteful because unless the generator is generating perfect images, the critic still has some information about the difference between the real and fake images. And it seems that if we're throwing our critic away, we're losing this information. And this seems the wrong thing to do. So a generalized energy-based model improves on GANs by taking the critic and involving the critic in the generation process. And what we found is that this, always helps. Unless our critic is basically a null critic, a critic with no information, you're always going to get better samples by including the critic. Okay, so I just remind, I think, everyone what a generator looks like for a GAN, because it's important to understand what it is that the generator is doing, or to characterize, let's say, the output of a generator, and to understand what this output looks like. So what a generator does for a GAN that's generating images is to take a low-dimensional source of randomness, like a 100-dimensional Gaussian, and then to push it through a bunch of transforms so that it basically covers a low-dimensional submanifold, I use that term informally, in a much higher dimensional ambient space. And ideally, that low-dimensional submanifold or subspace in this high-dimensional space is a set of plausible images. But what's, I think, important about the generator is that, very evidently, it's not generating samples with a density in that high dimensional space. It's covering a much lower dimensional subspace in that high dimensional space. And so any understanding of how to improve the generator samples by using a critic needs to keep this fact in mind. Okay, so let's now look at a toy example, which is the simplest instance that we could think of a generating, or of a problem setting, which, let's say, demonstrates all of the properties of this GAN. Okay, so our goal here is to create a target distribution P, which has the following form. Okay, so there's two things going on. It's in 2 dimensions, but it's supported on a 1-dimensional submanifold in those 2 dimensions. And the density on that submanifold is non-uniform. So you can see that the density is greater towards the end of the support here and here, and then lower in the middle. Okay, so our goal here is to generate samples which follow this support, or follow this distribution. Now, a first approach would be to use a classical energy-based model. Now, a classical energy-based model requires the x to have a density with respect to the beg on this space. So here I've written it as p of x is proportional to e to the, or x of minus e of x, where e is my energy function. And I'm assuming that I can integrate that energy function over my space. And what you see here is that because I've required my p of x to have a density with respect to the beg on this 2D space, I'm getting a blurry function which is trying to match my support. Okay, Now, this blurriness in 2 dimensions might not matter too much. But if I'm in much higher dimensional space and I'm trying to generate plausible images, this blurriness is fatal. So I'm getting, in this case, perhaps some very poor quality images. And in fact, the whole point of a GAN is to get around this problem by generating samples which are, by construction, on a lower dimensional subspace in this higher dimensional space. But this energy function is still something which is helpful and that we should keep in mind. Now, here is an instance of a GAN. Okay, so a GAN takes a low dimensional noise source, in this case a 1-dimensional noise source, and maps it to a higher dimensional space, in this case a 2-dimensional space, but covering only a support on a submanifold in that space. And here we've limited the capacity of our generator deliberately in such a way that it's able to match the support, but it's not able to match the density on that support. So you can see that the density on the support is uniform. Okay, so the question now becomes, given that my GAN is able to do that, how do I then improve it so that it matches my target? And what I might be able to do is to use this idea of the energy function, but just to use it as a reweighting function for the points on that support. So if I've got my energy function and I reweight the points on my support using this energy function, I've then been able to match the target distribution. So I'm sort of taking the best of both worlds. I'm using the energy function to reweight my GAN to improve it, but I'm using my GAN to get a low dimensional support in a high dimensional space. So is that idea clear? Okay, so I still have a mystery, right? The mystery is I've talked about this energy function. How on earth do I learn it? And I've also used some foreshadowing earlier. I said that the critic function of my GAN is somehow going to improve my sampler. So clearly the critic function of my GAN and this energy function have something to do with each other. But the mystery is what? Okay, I haven't said what. So that's the theme of the following slides and what you should all have in your be ready to see. All right. So let's formalize what I've talked about in the previous slides. Okay, this is my model. My model Q has 2 components. One is my GAN generator, and one is my energy function. My GAN generator does the following. It takes a source of randomness, a low-dimensional source of randomness, pushes it through some set of transforms parameterized by theta to get an X in a high-dimensional space, which is the output of the GAN. Then given the samples in my high-dimensional space, I'm going to reweight them using this energy function, and that is going to be my output. Okay, FQE is going to be this energy function, which I'm only going to evaluate on the support of my generator. And this is the distribution. Okay, so I've got a density here with respect to the Q theta support. Now, if Q theta had a density with respect to the veg on X, then I would just have my standard energy-based model again. But that's kind of boring. This is not the case I care about. All right. So now let's look at what this looks like on our example. So here's the target distribution. Remember that there are more points to. There is a question.
Yeah, I'm sorry. Can I ask you something? About so when you say reweight, does it mean that you discard a certain probability?
Very good question. That would be a terrible idea because important sampling is
could be costly,
right? It could be costly. So further foreshadowing, we don't do that. We do something hopefully cleverer. Yep. Because indeed, if I tried to do important, if I was doing rejection sampling or something like that, I would be like spinning my wheels. I'd be wasting a lot of computation for a very poor outcome. So we have this idea of reweighting in our head, but this is not what we do to implement this. Very important. Yep.
Thanks.
Okay. So here's our target distribution. More samples towards the end, fewer samples towards the middle. Here's our generator. It's got the correct support in this case, right? I'm going to say first that I've got the right support, but I've got the wrong mass. I placed the uniform mass. Okay. Now here's my energy function. I've plotted it on a log scale here, and I haven't told you how to get it. I've just said that I've solved it using magic at this point, but I'll explain later how I got it. But what this energy function is telling me is to increase the mass here and to reduce the mass here. Okay, notice that the energy function is defined over the whole space, but I'm only evaluating it on the red support. This is a very important point, right? My energy function is defined over all x, even though I'm only evaluating it on the support of the red. Okay, and ideally, if my energy function is converging, it's doing importance weighting. So it's basically taking the ratio of Q to P on the support that they share in common. Now, here is why generalized energy-based models are generalized. In practice, the GAN will never hit the support of P. It'll get close, but it won't hit the support. So here is basically what happens in 2D in any practical setting. The GAN will get everything wrong. It'll get the support wrong, and it'll get the mass wrong. Okay. Hopefully, though, it'll get the support reasonably close to where it should be. Now, in this case, the energy function is still defined over the whole space. And if I evaluate that energy function on the red, it's going to still tell me to put more mass towards the end and less mass towards the middle. So it's still going to improve my GAN sampler to get it closer to my target. So this is, an energy-based model requires the ratio of P to Q to be well defined. A generalized energy-based model doesn't. It doesn't matter that the support of P and Q don't match. I can still learn an energy function, and I can still use that energy function to improve my sample and get it closer to my target. So when I say generalized energy-based model, this is what I mean. Are there questions about this? Because this is, in a sense, like the most important slide of the talk. Okay, so if questions arise, I'm happy to answer them later. Let's talk about how to learn this energy function. And in particular, what does this energy function have to do with a critic function of a GAN? How do we learn the energy E? Okay, so what we're going to do is to fit a generalized notion of log likelihood, which is the integral of log FQ over P. Okay, so I can express this, I can define this, and it's minus EDP minus log ZQE, where ZQE is my normalizer, right? The thing that ensures that when I integrate my density over the support of Q, that I get a density that integrates to 1 over the support of Q. Now, let's first of all say that the ratio of P to Q is well defined. So either they are both with Lebesgue densities on RD, or they both share the same low dimensional support in the high dimensional space. Then this bound becomes tight when E is the negative log ratio P to Q. So no surprises here, I'm just doing importance reweighting. However, we're interested in the case where P and Q have disjoint support, so mutually singular. And as long as E is smooth over my space, over my ambient space, this is still well defined. It's not infinity or something vacuous in this case. Okay, so we're fitting this generalized log likelihood, but this doesn't look like a critic function. Okay, let's rewrite it here. So here is my generalized log likelihood minus EDP minus log e to the minus EDQ. This part looks like the critic function from before, but this part doesn't. So this leads to the very last trick, which is that I can lower bound minus log e to the minus EDQ by the following expression here for any real number C. And this expression here becomes tight when C is my normalizer. So it's a scalar C. When C is log some x of minus E, this bound becomes tight. So let's substitute in this lower bound. And here I've got minus E plus CDP minus e to the minus E plus CDQ plus 1. And now this is the KL. So basically like a lower bound on the generalized log likelihood, and remember we're maximizing this lower bound, is the KL divergence, so the critic function from the GAN from before. So that means that if I have GAN critic, which is a KL critic, then the function that I get out, this smooth function that I showed before, is the energy function that I showed a couple of slides ago. And this is how I obtain it. So my critic gives the energy function that I can use to reweight my generator. and get better samples. Are there questions about that? Okay. So basically, like, I'm alternating training my generator, my critic. For my critic function, I use a KL, and then I use the witness function for my KL as an energy, and this improves my model. Okay. Actually, this one, I'll talk briefly about this. So I've sort of talked about alternating training my generator and my critic. Let's say that I've trained my critic function to convergence. So let's say that I've learned this energy function here. Then I can optimize the parameters of my generator by gradient descent. And my estimate of my gradient uses my energy function that I've trained to convergence. So basically, like, if I train my energy function to convergence, then I can do a gradient step on my generator parameters. And this is all legitimate, subject to a whole bunch of smoothness constraints, which I won't go into. What we do in practice, of course, is not to train the energy function perfectly, but to train it well enough. So we take like a few steps of energy function gradient, and then we take a step for our generator. And we sort of alternate these two, and then we get our result. Okay, so the very last slide in the, well, let's say theory section is this question of how do you sample from this model? So a terrible idea would be like, to let's say throw samples away. We do something which is a little bit smarter than that. So here's our model, right? Where we've got FB of E, it's a function of Q, our generator, and our energy function. Now, what would happen if I used this model to take the expectation of a function of X? What would that look like? Okay, I would have G of B of Z, weighted by F, evaluated at B of Z, integral over eta of Z, dZ. So this means that, by this expression, we can define a posterior distribution over Z, which if we sampled from it, would give a distribution over these Z variables equivalent to, the distribution that gives us this expectation, right? So this distribution here, eta Z, FBE, BZ, if I could sample Z from that, that would amount to sampling Z from eta, pushing it through B, and then reweighting it with E. Is that clear?
So, I mean, I find this interesting. So,
yeah. So please ask.
Yeah. So it seems that sampling in this way will only allow you to sample expectations. And
right.
And so in other words, you're not generating the full distribution. You're creating a method to generate expectations, but not any nonlinear functions of the distribution. Or something like that.
So I guess it depends on, let's say, if we choose a sufficiently rich class of test functions, and we're able to ensure that over that set of test functions, we get the target distribution, that we get the expectations matching, then that should ensure that the distributions also match, I think.
Well, so maybe I interrupted you too early. You should finish your story. But I got the impression that you were still going to sample, let's say, generate the original points, which have maybe the right support, but not the right density, and then simply kind of post-process any expectations using.
No, so this is the magic. So basically, like we say, we don't first generate eta according. We don't first generate Z according to eta and then post-process. What we do is that we use our favorite Langevin diffusion algorithm to sample from this distribution, actually. So we don't sample from eta, we sample from eta times F BZ, which basically means that we, like say, oversample the Z latent space locations with a high E and undersample the parts of the Lie latent space with a low E relative to where the samples would be were I to use just the unmodified eta.
Now I understand. Okay.
Yep.
Thanks very much. Yes.
Yep. So this is, this is obviously like vastly more efficient than importance reweighting. And there's endless like kinetic Langevin samplers you can use, so we can choose like your favorite sampler to do this. But yeah, this is what we do. And so we're not throwing away samples. Yeah. So yeah, so we sample from our model basically by modifying the latent space using this energy function, and then sampling from that modified latent space, and then just pushing those modified samples through our B, and that gives us like some really nice samples, yeah, which are improved over the samples you would get from a GAN, because a GAN just uses this unmodified eta, and we already know we can do better. Okay. So it's always nice to show some pictures since we're coming to the end of the talk. There are sort of two things to keep in mind. One is that I made a claim that we can always do better using the energy function. On the y-axis here, I've shown a score which measures the quality of samples. Lower is better. 100 is what you get without the energy function. We always do better. I mean, it's not a surprise. I mean, as long as our energy function is not flat, we're going to do better. And indeed we do. There's also some heuristics we compare with, which I won't go into. The other fun thing is you can sort of run your sampler in your latent space, your Langevin sampler at a lower friction, and you can sort of see yourself exploring the latent space in the space of output images. So as I move my Z around my space, as I sample using this HMC sample, I sort of move from mode to mode, and I get something that goes from like truck to outdoor scene to nature scene and so on. So this is quite a nice property of this. Yeah. If you're sort of trying to explore the space of images that are sort of plausible according to our learned model. Yeah, so I think that concludes the talk, and we are also at the end of our time. So yeah, so this is a generalized energy-based model. It's using the Critic function, which is a Critic function deriving from a phi divergence as a way of improving the generator samples. And we've made the code available so you can try this for yourselves. I'll also say that this is sort of an idea which has appeared, I think, in related form many times recently. And so in effect, it's an idea which has become quite popular, which is this idea of sort of modifying the latent space of a GAN to get better samples out. So our two papers here actually came out within, like, I think 2 weeks of each other. This paper here by Mila in Montreal uses actually the Jensen-Shannon rather than the KL to get the energy function, but apart from that, same idea. And then these other two papers came out as well a little later, and they're building on this idea a bit further. So yes, I think it's something that a lot of people have independently found works well. So yeah, so that concludes the talk. So thank you.
Okay, thank you very much, Arthur.